These little LCD modules are extremely common, but what's it take to hook one of these up and get it working? Well, it's got these 16 pins that are used to interface with it, so if we just feed the right signals in, we ought to be able to get it to do something. And I've got this little computer that I've been building that so far I've just programmed to blink some lights. But now instead of using these signals just to turn these LEDs on and off like this, let's use them to feed in whatever needs to be fed into this display to make it do stuff. So let's hook that up. So let me get these LEDs out of the way, and I'll get the resistors out of here, and I'll install one of these LCD modules. And these come in different colors. Blue is pretty common. I'm going to use the yellow one just because I think it shows up a little bit better in the video. But I'll start by hooking up power to the display. So these first two pins are for 5-volt power, and VSS is ground, and then VDD is 5 volts. So that's the power for the module. And so the next pin here is V0, and that's for adjusting the contrast of the display. And really all we need to do with it is tie it to ground through a resistor to set the contrast. So I'll use a 10K variable resistor so we can adjust the resistance to adjust the display contrast. And I've already got the ground line here, so I'll hook one leg of this up to that ground. And then the middle pin will hook over to the V0 input. And now we should be able to just turn this and adjust the display contrast. And then the rest of the pins here are just the signals that we'll have to hook up to the computer's I/O lines here in order to communicate with the display. Except for the last two pins, A and K here. Those are actually for the backlight for the display, so the display lights up. And A is the anode for the backlight LED, so I'll hook that to 5 volts. And K is the cathode, so I'll hook that to ground. And we can hook this directly to 5 volts like this because the module's already got a current limiting resistor in it, so we don't have to worry about blowing up that LED by putting too much current through it. So we can hook it directly to 5 volts. Now we still haven't hooked up any of the signals, so it's not going to really do much yet. But let's power it on anyway, just to I guess sort of make sure. And the backlight works, so that's good. And nothing's on fire, so that's also good. And we can check the contrast setting too. So because that ought to work. And so there we go. So this is obviously maybe too dark, and if we go the other way, that's maybe too light. So if I kind of set it somewhere in the middle there, that's probably about right there in the middle. So hopefully if anything were on the display, we'd be able to see it. But of course, we're not sending anything to the display yet, so it's probably good we don't see anything there. But let's hook up the data lines so we can actually send data to the display. So you can see there are actually 8 data lines here, so D0 through D7. And so I'll just hook up all 8 of them to the 6522 interface adapter here. And I'm hooking these up to the same 8 bits that I originally had those LEDs hooked up to because we know we can set those pins to whatever we want. And actually I technically don't need to hook up all 8 of these. The display actually has a mode where you can do everything with just 4 data bits, which is a nice feature because it means we wouldn't have to hook up as many wires, or we wouldn't need to use as many pins on the 6522. But the 8-bit mode that I'm hooking up here is a bit simpler to use, so I'll start there. But maybe if you're doing a project like this yourself, and you can get all the parts over at eater.net/6502, but whether you get the parts from me or somewhere else, if you're doing a project like this, you might want to try figuring out for yourself how to do it with just 4 bits. But the 8-bit mode is a good place to start because that is going to be easier for us to use. And either way, there are also a few control signals that we need to hook up. So this RS, RW, and E pins are additional control signals that we need along with the 8 data lines. Now, fortunately, the 6522 interface adapter that we're using has 2 8-bit I/O ports that we can use. So we can just hook up these 3 control signals to 3 more I/O port pins over here, and we'll be able to control all the things. So I'll hook up this E pin, the RW pin, and the RS pin. And so those are all the pins we need to hook up. But what are these pins even for? Well, we need to dive into the datasheet to figure out how this all works. And this is actually the datasheet for the interface chip on the module. So it's underneath this blob here. It's not the datasheet for the entire module, which actually means we don't really care about half of what's in here, because on one side, we're talking to the chip through this, the 8 data signals plus these control signals, RS, RW, and E that we just hooked up. But the other side of the chip actually talks to the actual LCD screen. And so it's got a whole bunch of pins. And so, the chip itself has tons of pins that we don't really need to worry about because most of them are these like common and segment pins that go off to the actual display. And control which pixels on the display are set. And actually the display that we're using, 40 by 16 isn't even enough. So there's actually a little expansion chip here as well. And so there's extra pins that interface to that expansion chip, but we don't have to worry about any of that because someone else has built this module and taken care of figuring that out. So we can just ignore, roughly half of what's in this data sheet and really just focus on this interface here that we're connecting to. So if we look at this MPU interface, and MPU is microprocessor unit, which, we're building a microprocessor computer, then we see the 8 data lines that we've hooked up. as well as the RS, RW, and E signals that we also just hooked up. And the way this works is we've got these 8 data lines going in, and those 8 data lines either access the data register, which stores 8 bits of data, or the 8 data lines can access the instruction register, which also stores 8 bits of data. And the way we select whether we want to send data to the instruction register or the data register is with the register select signal. That's what this RS is, register select. So if register select is 0, then any data we send in here is going to go to the instruction register. And so that might be where we send commands to initialize the display or clear the display or move the cursor around, things like that. But then if register select is high, then the data that we send goes into the data register. And that would typically be how we send whatever characters we want to actually appear on the screen, because then that goes into the data display RAM, which stores all of the characters that are currently on the screen. There's also a read-write signal, so we can actually read information from the display module too. We aren't just writing to it. So for example, we could read what's in the data registers to get data out of the display RAM, or we could read with register select low, and actually we wouldn't read the instruction register. When register select is low, we actually end up reading the address counter as well as the busy flag. So those come out as well. So there's some data we can read and write. So we have a read-write flag there. And then finally, the E pin is the enable signal. So for any of the reading or writing we might do here that I've been talking about, the actual read or write doesn't happen until the enable signal is toggled high. So that's going to be important. So let's look at the assembly code we're using to control these signals. So this is the program I had running, and it puts a pattern of 50 hex out on the 8 bits that we had there. And then it uses this rotate right instruction to shift the bit pattern over each time through this loop here. But first, it initializes the I/O interface chip. That's what these first 2 lines here are. So this address 6002 is the data direction register that says whether these 8 bits here on the right that we're using are, or whether we're using those for input or output. And so by storing FF in that register, we're saying that those signals are all outputs. And actually, we can make this a little bit clearer by defining symbols for these different addresses. So instead of just saying 6002, we can define some symbols up here. So port B is at address 6000, and port A is at address 6001. And port A is the 8 bits on the left here, so we're just going to be using the top 3 of those bits. And then port B is the 8 bits here on the right that we've got hooked up. But then in the code, once we've defined those addresses, here instead of saying store A 6000, we can say store A port B. And so this is the same as it was before, but hopefully maybe a little bit easier to make sense of. And then the data direction register for port B is at 6002, and the data direction register for port A is at 6003. So now I can change this to store A DDR-B, to make it a little bit more clear that this FF is setting the direction of the data for port B. And then if I want, maybe it's not clear what this FF even means. Because what we're doing is we're loading FF into the A register, and then we're storing that to address 6002, which is the data direction for port B. But the reason we're using FF is because FF in binary is just 8 ones. So if we want, we can actually write out the binary to make it even clearer. So instead of a $, if I use a %, that means the number is binary. So I can just have 8 ones, and then that's going to be the same number as FF in hexadecimal. And then here, maybe it's more clear that each of these ones indicates that that particular bit should be an output. And of course, it never hurts to add a comment explaining what we're actually doing. And then for port A, we can actually do the same thing. But here we just set the top 3 bits as ones in order to configure just those first 3 bits as outputs. And then if we store this to the data direction register for port A, that'll set just those 3 bits on port A as outputs. And so here we're setting just the top 3 pins on port A to output. So that sets just these first 3 pins here that we're using as outputs. Now there's still another 5 pins here that are part of port A that we're not using. And we could configure them as either input or output. And because I left those bits as zeros in the data direction register, I'm leaving them as inputs, not outputs. But we're not using them right now, so it doesn't really matter that we're leaving them just as inputs. But anyway, now that we've got all these pins hooked up and we've got them all configured as outputs, we can start sending instructions and data to the display. And if we look back at the data sheet, we can see all of the different instructions we've got. So like clear display, return home, entry mode set, and so on. And of course, all these instructions have the register select signal set to 0 because that's how we tell it that we're sending it an instruction. If register select were 1, then we'd be actually sending data to the display. But register select 0 is for instructions. And then, of course, the read signal here is also 0 for all these instructions because we're writing to the display when we send it instructions. And then the instruction itself is kind of encoded here based on where the first 1 is in the data. And so all of these instructions start with some number of zeros followed by a 1. And so if it's 7 zeros followed by a 1, well, that's the clear display instruction. If it's 4 zeros followed by a 1, then that's the display on-off control instruction. And so you can see like the earlier that the 1 appears in the instruction, the more room there is after it for parameters that kind of go along with that instruction. So the clear display instruction, for example, that's all that's all zeros with a 1 at the very last position. So there's no room for extra parameters, which is fine because for a clear display, there really isn't any parameter. You do a clear display and it clears the display. It's not that complicated. But for the display on-off control, there's 4 zeros followed by a 1, and then there's room for 3 parameters. So there's a bit here that can be a 0 or 1, depending on whether you want the display on or off. And then there's a bit for whether you want the cursor display on or off. And then there's another bit for whether you want the cursor to be blinking. And so you can actually set all 3 of those as part of the display on-off instruction. But what instructions do we actually have to send to get the display to work? Well, if you flip a little bit further back in the instructions here, or in the datasheet here, I should say, they give some examples. And so it's probably easiest just to find an example that seems kind of close to what we're trying to do and then try to figure it out from there. And so this example here is for 8-bit operation, which is what we're doing. And then it's a 8-digit by 2-line display. And of course, we've got a 16-digit by 2-line display, but I don't think it's actually going to make that much of a difference. And this is sort of the closest example that's in here. But either way, I'll walk through the example and actually try to understand what everything's doing in here rather than just kind of blindly following the example and hoping for the best. So, let's start here with step 1. So step 1 is just powering it on, and then it's initialize no display. Well, we've gotten that far, so step 1's a success. And then step 2 here is function set. So it says it's setting it to 8-bit operation, and it's selecting a 2-line display with a 5x8 dot character font. And so for this instruction, we've got register select as 0, and we're writing. So those 2 zeros means, this is an instruction. And then the last 8 bits here are the actual data that we're going to send to send the instruction. And so the 001, that's sort of the first part up to that first one, that actually tells us what instruction it is. So 001 is the instruction. And then we've got the parameters here of 1, 1, 0, and then the last 2 bits it says it doesn't care. So when we flip back, we can actually find that instruction in that table we were looking at before. So it's an instruction here with 001 as the instruction. So that's what we were just looking at. And then it says we've got these 3 parameters that we can set. So DL is the data length, N is the number of display lines, and then F is the character font. So we can see over here on the next page, DL, if we set it to 1, that means we're using an 8-bit mode. And if DL is 0, we're using 4-bit mode. So we're using 8-bit mode, so we want to set that to 1. N is the number of lines on the display. So if we set that to a 1, we've got 2 lines. If we set that to a 0, it's 1 line. And then the font is either 5x10 dots per character or 5x8 dots. So that's just how many pixels make up each character. And, we really don't have a choice here, either with the number of lines or the number of dots, because the physical display we're using has 5x8 dots for each character. So it would look wrong if we tried to use this 5x10. So if we go back to the example, see 001 is the instruction, and then we're setting 8-bit mode, a 2-line display, which is what we've got, and a 5x8 character font, which is also what we've got. So that all sounds like what we want. So let's send this instruction to the display. So again, the instruction itself is 001, and then we're going to have a 1 because we want 8-bit mode, and then a 1 for the 2-line display, and then a 0 for the font, which we want the 5x8 font. And then the last 2 bits aren't used, so I'll just set those to zeros because this doesn't matter. And so this is the instruction to set 8-bit mode, 2-line display, and a 5x8 font. So I'll put that in there. And then we can put this out on port B. And so that sets these 8 data bits out on port B here. But we also need to set the register select bit as 0 and the read-write signal as 0. And those are over here on port A. So we need to make sure we set those as well. So if we just load and store a 0 to port A, that'll clear the register select, the read-write, and the enable bits. And then to toggle some of these bits, what I can do is I can define some more symbols here for each of the control signals. So the enable signal is the top bit on port A. And then the read-write signal is the next bit. And then register select is the 3rd bit, like this. So if we go back down here and take a look at what we've got so far, we're putting our instruction on port B here, and then we're clearing all of the control signals. And so in order to actually send the instruction, we need to toggle the enable bit. So what I can do is load just the enable bit into the A register and then store that into port A. And so that'll turn the enable signal on. And then if we immediately set it back to 0, that'll turn it off again. So this effectively will just toggle that enable signal on and off really quickly, which will have the effect of telling the display to then accept this instruction that is sitting on the data pins. So effectively, all of this ends up sending this instruction to set the 8-bit mode 2-line display 5x8 font. And of course, this here is where we're setting the enable bit to actually send the instruction. So all of that is just for this step 2 here in the initialization example we've got. So that sets the function. So we've got our display set in this mode. So then the next thing in the example here is the display on or off control. So again, this is sending an instruction. In this case, it's 00001. So 4 zeros and a 1 is the instruction. And then there's 3 parameter bits here. So if we go flip back and look at the instructions, we've got, 4 zeros and a 1. That's going to be display on-off control. So 4 zeros and a 1 is the instruction code there. And then the parameters we have are, do we want the display on or off? Do we want the cursor on or off? And do we want the cursor to be blinking or not? And if we go back and look at the example, in their case, what they're saying is they want, the display to be on, makes sense. The cursor to be on, which, it's up to us whether we want to see that or not. And then cursor blinking is off. And that all sounds fine to me. So let's send this command. And so what I'm going to do is actually just copy what we've got here. So all of this sent the first command. So I'm going to copy that and then paste it down here. So I've got a second copy of that, except here the instruction is going to be 4 zeros followed by a 1. So this is the instruction. And then the 3 last bits here set the different things. So we want display on, cursor on, blink off. So we'll set that as a 0. So this is going to be display on, cursor on, blink off. And we're sending that to port B. That's our data lines. And then same thing here. We're starting with 0 on port A, and then we're toggling that enable bit to send the instruction. And so now that should take care of step 3 here. So we've got our display turned on, our cursor on, and it's not blinking. So then step 4 is entry mode set. And so here again, we've got register select 0, read write is 0. And then the instruction is going to be, let's see, 1, 2, 3, 4, 5 zeros followed by a 1. That's the instruction. And then there's 2 bits here at the end where we can set parameters. And it says this is setting the mode to increment the address by 1 and shift the cursor to the right at the time of writing to the display data or character generator RAM. Display is not shifted. So what does all that mean? So let's look at what this instruction is. So it's, 5 zeros followed by a 1 is the instruction, and there's 2 parameters. So if we flip back here to the instructions table, that's this cursor display shift. So again, we see, nope, that's not it. Entry mode set. So we see 5 zeros followed by a 1. So that's the instruction itself. And then there's a bit for ID, and then there is a bit for S. So what are those? So it sets the cursor move direction and specifies display shift. And it's performed during data write and read. So what does all that mean? So ID is, increment or decrement. So what are we incrementing or decrementing? Well, to understand what this is doing, we've got to look back at the block diagram, or maybe it's helpful to look at the block diagram here. So remember, we're talking to this interface through the 8 data lines plus these 3 control signals. And so far, we've just been sending instructions in here, and those instructions go into the instruction register, and there's some decoder, and there's some logic that deals with all that. But eventually, we're going to be sending data to this thing and actually displaying stuff on the screen. And so when we send that data, that goes into this data register, and then ultimately gets transferred into the display data RAM. And this display data RAM has got 80 bytes, essentially, so it can hold up to 80 characters of stuff that's going to end up displayed on the screen. And so if this has got 80 characters of storage space in it, and there's potentially up to 80 characters on the screen, depending on how it's hooked up. In our case, there's only 32 characters on our screen, but that's just the hardware we've got. But in any event, if there's potentially 80 bytes of data in here, and we only have 1 byte where we're sending data to it, how does it know where to put that byte in memory, and therefore how does it know where to put that character that we're sending on the screen? Well, to do that, it's got an address counter. And so effectively, when we reset this thing, the address counter is going to say, the next character you send is going to go in the top left position on the screen. It's going to go in that first character. And so when we send a character, it's going to put it in RAM in the right place so that it will appear first on the display. Then if we send it another character, what we'd like to do is have that character then go to the next position on the display. And then if we send a third character, that should go to the third position on the display. And so each character we send just shows up in the next position on the screen, so we can just type out text. And in order for that to work, what we want is that every time we write a character, this address counter that keeps track of where that character is going to go on the screen, we want that address counter to increment each time we write a character. And that's actually what we're setting with this next instruction. So if I can find the page where we had those instructions, here we go. Entry mode is when we enter data into it, what mode is it in? What is it doing? So this increment or decrement says, do we want to increment that address register each time we send a character, or do we want to decrement it? And so essentially what that's saying is, like, when we write a character here, do we want the next character to be written to the right of it, or do we want to be writing backwards? So if we had this as decrement, then each time we wrote a character, it would decrement the address counter, and the next character would then go to the left of the previous character. So it seems like the normal scenario there would be, we want characters to go, left to right. So we want that to be incrementing. And then S is, what was that? That was accompanies display shift, which I believe what that means is that you can have the entire display shift over. And so even though you're incrementing the address where you're putting the next character, the entire screen can shift the other direction, which might make sense if you get to the end of the display and you want it to scroll. But in our case, the example that they have here, they're setting it to increment and they're setting it to not scroll. And so that sounds like it makes sense to me. So again, we want to send another instruction. So what I'll do is I'll just copy all of this code again to send another instruction. And in this case, the entry mode is 5 zeros followed by a 1. And then we have two parameters. One is we want to increment the address register each time we write a character so that the next character that we send goes next to it. And then we don't want the display to scroll. And so we're incrementing and shifting the cursor each time, but we're not shifting the entire display. Okay, so now all of this sends that instruction. And so that's step 4 in this example here. And so the next step, step 5, is actually writing data to the data display RAM, which looks like it should actually put a character on the screen. So in this case, one thing that's different is the register select is now 1, because we're not sending instructions anymore, we're actually sending data. So that's the other register. So we want to set register select to 1, and then we're still writing, so the read-write signal is still 0. And then the data here, this is actually just the binary representation of the letter H. So let's do this. So now the data we want to put out there is that letter H. So we could do the binary representation of H like this, but instead what we can actually do is just put the letter H like that, and that's going to do the same thing because the assembler is going to know that H is represented as that particular binary sequence in ASCII. So we can put that H then in port B, and then just like before, we need to actually toggle that enable signal. So I'll copy that code down here. So we're loading the H, and then we're toggling enable, but we also need the register select signal to be a 1 because we're sending data, we're not sending an instruction. And so here we want register select to be a 1 before and after we toggle enable, but also when we toggle the enable, we also need the register select to be a 1. So what we can do is we can say register select bitwise OR with the enable, and that'll basically set both of those bits. So here we have just the register select bit set, here we have the register select bit and the enable bit set, and then here we have just the register select bit set. So this will keep the register select bit set and toggle the enable on or off, which will send the data on port B to the data register. So it should send this H now to the display. And so that's everything we've got here up to this point where we're putting a character on the screen. And it says, we can basically continue to do that to continue to write other characters to the screen. But let's just try this out and see if it works so far. So at this point in our code, once we've written that H to the screen, we actually don't really want to do anything in the loop. So if I just have a loop and then jump to loop, this will essentially just halt the program because it'll just throw it into an infinite loop. So once it gets to this point where it puts the H on the screen, it'll just sit here and loop forever and not do anything else, either good or bad. So let's save that, and then I'll go over and assemble it. And I'm going to use VASM, and we want to create a binary file, and we're using dot directives. And then the file is helloworld.s. And so there we go, that compiles it. So if we want, we can take a look at the contents of that binary file that it created. And I guess if you wanted, you could check and see that it did everything right. It looks like it's, doing a load A FF and then a store A to 6002. And you could pick this all apart if you really wanted to. One thing that sort of jumps out to me is I see the H there for the actual H that we're going to display on the screen. So that appears in there. Let's go ahead and get this put on the EEPROM. So I'll pull the EEPROM out of here, put that in the programmer. And we've got an AT28C256 is the EEPROM we've got. And we're going to write the a.out file. And there it goes. It's written. And there it goes. And so now we'll stick this back in the circuit. And let's power this up. Reset it. And we have a cursor and an H. Hey, it worked. So we're able to print something to the screen. And it's this code here that's actually printing that H. So that's this block of code here. We're putting the H out on the data port. And then we're, well, actually the comment's wrong here. We're setting register select because it's the, setting that register select tells it that we're sending data. We're not sending an instruction. And then we toggle the enable bit on to actually send the instruction. And then here we are basically just clearing the enable bit. So if all of this works to send the character H, the quick and dirty way of sending more characters would be just to copy this code and add more letters. So if I wanted to print the message, hello world, it might not be the cleanest way or the most efficient way to do it, but I could just copy this block of code for each letter and send each letter just like we are here. So that's what I'm actually doing here. And I realize this is not the most efficient way of writing code, but that's okay because I just want to get this working. And then we can talk about how do we actually make this more efficient or make the code easier to read or things like that. So there we go. And definitely not proud of this code, but let me make sure I actually spelled this right. But here we're printing hello world. Definitely using a lot of code to do it, but it should work. So let's give this a try. I'll save this and then go ahead and reassemble it. And here, actually, if I do a hex dump, you'll see this is what I'm talking about by not being particularly efficient. This is all of the binary code for that program, and it's huge relative to what it's doing, just printing hello world. You can see the message is in there, but that's fine. At this point, I just want to get this working, and then we can talk about how to make it more efficient. So let's reprogram it. I'll pull the EEPROM out of here and put it back in the programmer. And then go ahead and program it. There it goes. Let's now put the EEPROM back in our circuit here and power it up. And I'll hit reset. And there it goes. It's printing hello world just like we expected. But I have to say, I'm not particularly proud of this code. It's 177 lines of code just to print the hello world message. And it compiles to 333 bytes of machine language code just to print the hello world message. I think we can do a lot better than that. And that's what I'm going to do in the next video is rewrite this to be a lot more efficient. But I'm going to do that in the next video since we're actually going to need to add some more hardware in order for us to write more efficient software. So that's what I'm going to get into in the next video. And remember, if you're interested in following along with these videos, you can get all the parts I'm using over at my website, eater.net/6502. I've got the base computer kit as well as everything else you need to follow along with these videos. So you can check that out at eater.net/6502. And of course, as always, I want to thank all my patrons. Your support is a huge part of what makes these videos possible, so thank you.